Here we're going to use Stokes' theorem to evaluate the surface integral over S of the curl of f dot ds. Our vector field is f of xyz is equal to x squared sine of zi plus y squared j plus xyk. S is the part of the paraboloid. Z equals 1 minus x squared minus y squared that lies above the xy plane, oriented upward. Now these instructions have used Stokes' theorem to evaluate the surface integral of curl of f dot ds really means that we're going to actually use the line integral over c of f dot dr. Here we have my best attempt at the paraboloid. It's the surface S. Oriented upward means that our normal vectors are pointing up. And if you were an individual walking along the curve with your head pointing roughly in the same direction as the normal vector, right? So upward oriented means your head is above the xy plane, and you're walking around the curve, then the region D that we've talked about before that's enclosed by the curve will be to your left. So the upward or downward orientation induces an orientation for C. Well, we said we're going to find the line integral over C of f dot dr, and so we need a parameterization of C. F dot dr is in one dimension, and so we're looking at r of t, and we're looking at a circle in the xy plane of radius 1. So r of t is equal to the cosine of t sine of t 0, where t goes from 0 to 2 pi. R prime of t is then the vector negative sine of t cosine of t 0. And f of r of t is then going to be x squared times the sine of z, but x is cosine of t and z is 0. We're going to write it down as cosine squared of t sine of 0, but we'll simplify that in a bit. Y squared is going to be sine squared of t. And then xy is going to be sine of t cosine of t. Now we're ready to find the line integral over c of f dot dr. And that's going to equal the integral from 0 to 2 pi. Now we take our dot product. Negative sine of t times 0 is going to give us 0. I won't write it down. Cosine of t times sine squared of t. I'll write that as the sine squared of t cosine of t. And then for the third component, 0 times, that's not a comma, that's a times. 0 times the sine of t times the cosine of t is 0. So we end up with a fairly straightforward integral. And using the power rule and a substitution, we get 1/3 sine cubed of t evaluated from 0 to 2 pi. Our result is 0, folks. What we actually found was the surface integral over S of the curl of f dot ds. The way we can interpret this is that with this vector field f, there is no net tendency for a fluid to rotate on this surface. And we figured it out by finding that there was no tendency of the fluid to circulate around the boundary.